Test, test, test. Okay, I have another problem here. This is going to be a quantum mechanics problem this time. This is problem 2.28 from the Modern Quantum Mechanics textbook by Sakurai, the third edition. So if you're using an edition earlier than that, this number might be different. So a particle in one dimension is trapped between two rigid walls, so the infinite square well. And at time zero, it is known to be exactly at x equals 1/2 with certainty. What are the relative probabilities for the particle to be found in various energy eigenstates? Write down the wave function for t greater than zero. You do not need to worry about absolute normalization, convergence, or other mathematical subtleties. So first, I'm gonna just draw a little picture of what this potential looks like. It's what is known as the infinite square well. So inside the well, potential zero, and outside of the well, the potential is infinity. Okay, so what we're gonna do is the first thing is solve for the um, time independent solutions to the time independent Schrodinger equation. And because it's time independent because the potential does not depend on time. So it looks like this at all times. So time looks like this, negative h bar squared over 2m. So h bar is Planck constant. M is the mass of the particle that's trapped between the two rigid walls. V is the potential. E is the energy of the particle. And phi is the wave function that we're trying to get the solution for. So there are two solutions to this equation. The first one is outside of the box, where the potential is at infinity. So if the potential is infinity, the only way for this solution for this equation to work mathematically is for phi equal to zero. So outside of the box, there's no wave function. It's zero everywhere. But inside of the box, the potential is zero. So this equation becomes this whole term here goes away. And now this is just a second order differential equation that's has the general solution. Let me just rewrite it. So first of all, the second derivative we can just note with two primes like that. And then we can introduce, okay, first we can move all the constants to one side. Like that. And then we can introduce a new constant called k, which is equal to the square root of 2m e over h bar squared. That way we can just simplify this a little bit. It looks like that. And now this, the general solution for is just sines and cosines. With constants, some constants out front. And I mean, we could check this really quick. The first derivative is a cosine minus b sine. Take the derivative again. Oops. Yeah, so every time you take the derivative, you get a factor of k from the chain rule. And that is equal to our original solution there. So this solution is correct, but we know we can do better than this because we know some more information about the boundary conditions. So we know that the wave function must be continuous. So that means the wave function outside the box and inside the box, they have to match. And we know that outside of the box, the wave function is 0. So this means that our boundary conditions are the wave function at x equals 0 and the wave function at x is equal to L must both be 0 because outside of the box, the wave function is 0. So if you plug these boundary conditions into our general solution, we get sine of 0 is 0, cosine of 0 is 1, so b must be 0. So this part goes away. And then the other boundary condition, phi at L is equal to a sine KL, and that also has to be equal to 0. And we don't want this constant a to be 0 because then the entire solution would just be 0. So a can't be 0. But sine KL is 0 when KL is equal to sine inverse of 0. And this can happen. So sine is 0 anytime uh, you have a multiple of pi. So or 0. So sine 0, 0, sine pi 0, and so on. So you get that k L is equal to n times pi. Or so we get that kn is equal to n pi over L, and that satisfies the boundary condition at x equals L, and that can actually happen an infinite amount of times, for any time you get for integer values of n pi. So that means we actually have an infinite amount of solutions, and those are what we call the energy eigenstates. So that's why I have this subscript n there. And we can even figure out what this A is, because we know that the particle has to be somewhere inside the box. So that means the probability of finding the particle inside the box is 1, which means that the integral from 0 to L, the wave function squared, uh, the complex conjugate times the wave function is equal to 1, like that. So we can just plug in. Okay, now this integral you can solve by using like Mathematica or integral calculator, and that's equal to all of this thing here is just equal to L over 2, and all that's equal to 1, which means that our A is equal to square root of 2 over L, which means we can update our eigenfunctions one more time, and we get that the energy eigenfunction is equal to square root of 2 over L sine n pi x over L. So probably have seen that before, but I just wanted to derived them once, so can use them now for this problem and for any other problems that we would need them for. So that was kind of just some background work. Now we're gonna start the actual problem. First, I need to add some more pages. Okay, so we can write the full time-dependent wave function now, which I'm going to write as capital Phi, like that. Depends on time now. This is equal to the infinite sum. Okay, so I'll make a comment about this index here in a second. Some coefficient times our time-independent wave functions that we just solved for, times e to the I. Oh, okay. Before I do that, there's one more thing I forgot to do. We said this k is equal to here we introduced a k. K is equal to square root of 2m re, which means that e is equal to k squared h bar squared over 2m, and so k is actually depends on this index n, which means that e also depends on n. And the kn we solve for as this here. So this E of n, those are the energy eigenvalues, and they go hand in hand with the energy eigenfunctions. And so this is equal to n squared, h bar squared, pi squared, divided by 2m L squared. Okay. And so, and again, n is some integer, positive integers from 0 to infinity. Okay, so now we can write the full time-dependent wave function as an infinite sum from uh, some coefficient Cn times the energy eigenfunctions times e to the negative I En times t divided by h bar. Okay. Now it's given that at time 0, it is known to be at exactly x is equal to L divided by 2. So if we plug in 0, we get just and this exponent will just be 1, and that's equal to exactly x is equal to L over 2. That's what we're gonna call this delta function. So yeah, so this means at time equals 0, the position is known to be exactly at x is equal to L over 2. So exactly in the middle of the box. And our objective is to find the full wave function for a time t greater than 0. And the probabilities for the particle being in various energy eigenstates. Okay, so the probability of it being in any given eigenstate is basically this coefficient here. So that this is an infinite sum over all the eigenstates. And so if C1 is equal to 1, for example, then it's completely in that eigenstate. But that, I mean, you can have, that doesn't have to be the case. You can have C 999 be equal to some finite number. And so we have to find exactly what these probabilities are. So we have to find a formula for Cn. And the way we're going to do that is by using, we know that the eigenstates form an infinite orthonormal basis. So which means that if you have an integral like this, where these are two different eigenfunctions, this is always going to be 0 if m does not equal m, and it's always going to be 1 if n is equal to m. Or in other words, it's equal to the delta function of m and n. So n and m have to be equal. And now we go back to, we take this relationship here. So And if we multiply both sides by another, so if we multiply both sides by another eigenfunction, m, and then we take the integral on both sides, we're left with something like this. Uh, the integral and the sum can always be exchanged because they are linear independent operations. So and the coefficient I'm also going to move because it doesn't depend on x, so I can pull it outside of the integral. And this integral is from 0 to L, just over the entire box. And so this here is the relationship we just worked on up here. So this is only going to pick out the values when n is equal to m. Which means that we now have a formula. So this sum goes away because we're only picking the one value when the delta function hits. So when n is equal to m. Like that. And then there's a couple things we could do to simplify this equation. First of all, the eigenfunctions are all real, so there's no complex imaginary part to it. Well, okay, so that means we can just drop the complex conjugate here. Yeah, I'm almost done, so I'm going to try and do it on this Zoom meeting. 8 minutes. Okay. So, and then the other thing we can do is this m is just a dummy variable, so we can just go back to n if we want. Just like that. And now we can plug in both of these things that we already know. So that is square root of 2 over L sine n pi x over L. And that is the delta function x minus L over 2. And when you have an integral over a delta function like this, where if this value is inside of your limits of integration, it just picks out this value for x here. So X is equal to L over 2. Okay, so let's put a box around. What are the relative probabilities for the particle to be found in various energy eigenstates? So that's exactly what Cn is here. I guess we can simplify this a little bit more. If n is even, you have factors of 2 pi n, and sine of 2 pi n is always 0. And so Cn is equal to 0 if n is even. And if n is 1, 3, no, that's 1/2 pi, that's 3 pi, then you go 5 pi. So basically this alternates between being 2 pi over L for n is equal to 1, 5, 9, and so on, and Cn being equal to negative, and being 3, 7. And if you work it out, you can simplify this even more to being, so Cn is equal to 0, n is even, and times negative 1 to the n minus 1 divided by 2 when n is odd. That's what this here means. But really, you can leave it like this, or like this is probably fine too. So now just the last thing we have to do is write the full time-dependent wave function. So we have all the pieces that we need to do that now. So that's the solution, and Cn is right there, so we have that part. We know what the energy eigenfunctions are, and just write those down one more time here so it's all in one place. So that's the full solution. Um, you don't have to, so the problem says you don't have to worry about absolute normalization, so you don't have to renormalize this, because technically you could, there could be another normalization constant here again, A, and you would have to do something like this again, but the problem says you don't have to worry about that. So that's your full solution. And yeah, I hope this was useful. Thank you very much for watching.